talking about our work on studying the stability of our tumbling robot, COBRA. My name is Adarsh Salagame. I'm a PhD student with Silicon Synapse Lab at Northeastern University, and I work with a large team led by Dr. Alireza Ramazani, who's an associate professor with the Department of Electrical and Computer Engineering. So this work is based on our multimodal snake robot COBRA. As you can see on the video on the top right, COBRA here uh, is performing a standard snake-like gait called sidewinding. But in addition to this, COBRA can also perform a rolling gait by raising its head and tail and locking them in place to form this wheel-like structure. The head contains this actuated mechanism, which once the head and tail are aligned with each other, these gear rotates, which pushes these fins out and into this cavity, which holds the head and tail together passively. And once this is held together, um, using very little energy, the robot can hold the shape and shift its center of mass within the shape to initiate tumbling locomotion. And the purpose of doing this is that since it's able to hold the shape with very little energy, we can actually travel really large distances down slopes purely under the effect of gravity and use very little energy to do this locomotion. So to enable this tumbling locomotion, we attached these outer casing on the robot, which partially protects the electronics of the robot, but also provides a large base, which provides lateral stability. And that has a twofold effect. So in this top video, what you're going to see is Cobra starting on a 4-degree inclined slope and shifting its center of mass forward to initiate tumbling. And the attachments do provide lateral stability. So despite the fact that it wasn't able to start rolling, it did maintain its vertical orientation. And with a slightly larger push and a larger slope angle, Cobra is able to consistently um, roll down the slope and maintain its stability without falling over. And the reason this is important is that we are trying to perform this locomotion in environments shown here on the bottom right, where it's a very rugged outdoor kind of environment, and you have several obstacles such as these bushes and rocks, which can potentially topple the robot as it goes through the stumbling locomotion. So our eventual goal is to build a closed loop controller that can allow the robot to follow a desired path down the slope. And in order to do this, we need to understand the stability of the robot and how much of an external perturbation it can survive while still maintaining its rolling stability. So that is the purpose of this work. In order to do this, we model the robot dynamics. On the right here, you see the frames of the robot. So we attach a coordinate frame to every link and every joint. The joint angles are defined by a position QI, where I goes from 1 to 11 for 11 joints, and a torque tau I. The position of the robot is identified by the vector to the head module, which is taken as the reference frame for the robot. So we define the vector and the position vector and the Euler angles to the head for the pose. So the generalized coordinates of the robot are defined as shown here. And from this, we can define the angular momentum of the robot and the kinetic energy. And continuing on this, once the robot is in the tumbling configuration, um, we can define the kinematics of the tumbling structure to identify the position of the contact point with respect to the position of the head based on the joint angles and the orientation of the head, and define the kinetic energy as a function of the angular momentum of the robot. So what this lets us do is control the angular momentum through controlling the contact point, and that lets us define a desired path. So in order to understand the dynamics of this tumbling locomotion, we built a simulator in MATLAB using the SimScape multi-body toolbox. And what you see on the video below is a model of COBRA, which in its tumbling configuration is rolling down a slope of 10 degrees. And we can track several useful data points, such as the position of the head, the joints on each, the torque on each joint, and the ground reaction forces on every link. And this is important because especially the ground reaction force is something that is very hard to measure on a robot such as COBRA, which makes multiple contacts on the ground over its locomotion. So use this test setup that lets us study the amount of force required to fully topple COBRA over. So this diagram shows the amount of change in angle it would take to make COBRA unstable. So it would have to tilt by an angle of over 10 degrees for the center of mass to go past this support structure on the ground. And to test this, we connected COBRA to an imaginary fixed link in the air. And we gave it a spinning moment. So this is rotating at a fixed angular velocity of 2 revolutions per second. And we apply a small moment about the toppling axis over a period of 0.1 seconds. 0.1 seconds is about the contact time that it would take for one link to be in contact with the ground during the stumbling locomotion. And what we see is that the torque required to affect a small 1 degree change in this axis, or the toppling axis of COBRA, is over 50 newtons. So what this gives us is a constraint on any future controller that would have to react to this external perturbation and remain stable. I've demonstrated open loop tumbling for the very first time and developed a simulation to study the tumbling dynamics within which we can read all these data points which are inaccessible on the real robot. And additionally, we have built a modeling framework for tumbling dynamics and investigated the natural stability of this tumbling structure. The next step will be to validate this dynamic model and build a control framework surrounding this that lets us steer the tumbling locomotion. And part of this will be to integrate onboard sensing to identify contact locations and estimate the ground reaction forces, um, and validate this by comparing it with those that we see in simulation. NASA's innovative advanced concepts